You have a function that takes 3 arguments. You call it once, pass all 3, done. But what happens when you only know one of those arguments right now and the other 2 show up later? In most languages you end up writing wrapper functions by hand. Lots of them. That boilerplate grows fast. Currying is the idea that instead of collecting all arguments at once, you collect them one at a time, each call returning a new function ready for the next argument. It is one of the foundational ideas in functional programming, and once you see it, you will spot its fingerprints everywhere. Here is the pain point currying solves. You have an add function, you call add of 2 and 3 and you get 5, fine. But now you want a specialized function that always adds 2 to whatever number you give it. Without currying you write a wrapper, const add 2 equals x arrow add of 2 comma x, that is boilerplate. You want 10 of these specialized functions, you write 10 wrappers. And there is a deeper problem, the original function demands all its arguments right now at the same moment. That rigidity makes functions hard to compose, hard to reuse, and hard to plug into pipelines. Currying dissolves that rigidity by transforming every multi-argument function into a chain of single-argument functions. The formal definition is straightforward. Curried function of arity n, where arity just means the number of expected arguments, is transformed into a chain of n functions each taking exactly 1 argument. Curry of add, where add takes n b, becomes a function waiting for a, which returns a function waiting for b, which returns the result. In type notation, a function from across b to d becomes a function from a to a function from b to d. The arrow notation in Haskell makes this completely explicit. In JavaScript and Python, you add this behavior manually, either by using a library or by writing a small curry helper. The transformation is mechanical, but what it unlocks is not. How does curry actually work internally? The implementation is clean. You pass your original function into curry. It returns a new function called curried. Every time curried is called, it checks whether it has received enough arguments to satisfy the original function's arity. If yes, it calls the original function immediately and returns the result. If no, it returns a brand new function that, when called, combines the arguments collected so far with the new ones and tries again. This is a closure. The inner function captures and remembers all the arguments it has seen. The chain terminates the moment the total argument count meets or exceeds arity. No magic, just functions returning functions with a length check in the middle. The most immediately useful thing currying enables is partial application, locking in some arguments now and supplying the rest later. You have a curried multiply function. You call it with 2 and get back a new function double that multiplies anything by 2. You call it with 3 and get triple. These specialized functions cost you nothing extra. They fall out of the curry transformation automatically. Partial application becomes the default, not a special case. This also makes pipelines natural. When you pipe data through a series of functions in functional code, each step needs to be a unary function, 1 argument in, 1 value out. Curried functions are always unary at each step, so they compose without adapters. Curry and function composition are designed for each other. The compose utility applies functions right to left, pipe applies them left to right. Both expect each function to be unary. Take negate, add 1, and double. With pipe, 5 flows into negate giving -5, then into add 1 giving -4, then into double giving -8. Without currying, if any of those functions needed extra configuration, you would be back to writing wrapper closures by hand. With currying, you partially apply the config argument up front, and the resulting unary function slots directly into the pipeline. The whole style of writing code as a sequence of transformations rather than a sequence of mutations depends on this. Different languages take different approaches. Haskell and Elm auto-curry every function without any special syntax. It is baked into how the language works. Every multi-argument function in Haskell is already a curried chain of single-argument functions, and partial application is just calling a function with fewer arguments than it expects. In JavaScript, you reach for a library like Ramda or la-fp, or you write a small curry helper yourself. Python gives you functools, partial for locking in arguments, though it is a slightly different mechanism, and full currying requires manual wrapping. The concept is universal. The ergonomics depend heavily on the language. Where does currying show up in real production code? React event handlers are a classic example. Without curry, you write an inline arrow function per field. On change equals e arrow handle change of email comma e dot target dot value, then another for name, another for every field. With a curried handler, you write handle of email and handle of name, and the function itself manages the rest. API query builders use partial application the same way. Curry the fetch function over method and URL, and get back specialized get and post functions with the method locked in. Validation pipelines curry rules over their configuration, producing named validators like required and min length 8 that can be composed into schemas without repetition. Currying is powerful, but it has real costs you should weigh honestly. For teams coming from object-oriented or imperative backgrounds, f of b of c reads as noise, not clarity. Partial application creates closure objects at runtime, which means heap allocations that a naive for loop would not incur. Stack traces from curried chains often show a series of anonymous functions, making debugging harder. TypeScript requires fairly involved generic overloads to type curried functions correctly. The honest decision process is 3 questions. First, am I repeatedly writing wrapper closures to lock in config arguments? If yes, curry. Second, do these functions need to compose with pipe or compose? If yes, curry. Third, will my team read this and understand it faster or slower? That third question matters as much as the first 2. Currying is the idea that every multi-argument function can be rewritten as a chain of single-argument functions, each returning the next until all arguments are collected and the result is computed. It is automatic in functional-first languages and manual but accessible everywhere else. It enables partial application, makes function composition effortless, and pushes you toward a style where configuration is locked in up front and data flows through pipelines of specialized, reusable transforms. Use it where it cuts boilerplate and adds composability. Skip it where your team will spend more time deciphering the chains than they gain from the reuse. Thanks for watching.